Hello everyone. This is Zhao Yu from UMass Amherst, and today Zed and I are going to present our progress in the multi-homing wireless access in vehicular environment project. And here's a list of the people working on the project. We have Professor R1 as the PI of the UMass team, and Zed and I are the PhD student in UMass Amherst, and we are both working on this project right now. Uh, the full team includes the Bas, Pandu, Chad, John, Rajesh, and Hamid. Since last fall, we've been discussing our progress on this project with the full team very regularly. Sometimes it's a weekly meeting, sometimes it's a bi-weekly meeting. And in this talk, I'm going to talk about a few things as shown here. So first, I will give a brief introduction to the background, including the state-of-the-art system for multipath communication, and also our system called MSocket. Then I will let Zed take over to show you a demo with an Android MSocket application. Then he will present the progress on the macro benchmark experiment, such as the overhead analysis, aggregated bandwidth efficiency analysis. Then I will take over again and present the MSocket performance in wild. At the end of the talk, let's discuss the future direction of this project. And I will leave like a few minutes for the questions. So first, multipath TCP or MPTCP. So MPTCP is a state-of-the-art system that enables multipath data transmission. It allows the simultaneous use of several IP addresses or interfaces by modification of TCP that present a regular TCP interface to applications, while in fact it spread the data across several subflows. As shown here, MPTCP is actually implemented in the Linux kernel, and it requires a Linux kernel modification to use it. All the applications are running on top of the operating system with the MPTCP enabled will automatically use the multipath communication. So MSocket is our system that enables the multipath data transmission. In contrast to MPTCP, MSocket is implemented in user space rather than kernel space. So no kernel space change is required to use MSocket, and since its current implementation is in Java, so it is supported on any platform that can run a JVM, for example, Mac OS, Linux, Windows, or Android. Meanwhile, MPTCP only works on the Linux systems, such as Ubuntu and Android. And MSocket is also more flexible compared to MPTCP. That means application developers can decide whether they want to use multipath data transmission for the app, but while for MPTCP, it's because it's internal implementation, so the developer must make the 0-1 decision about whether all the applications want to use the multipath data transmission or not. So, and the last advantage about MSocket is that it's reasonably easy to use, which I will show in the next slide. So let's take a look at how we can use MSocket for multipath communication. So MSocket communication abstraction is very similar to the traditional BSD socket API. So as shown here, the MSocket server first need to open the server socket on the server side and listen for the connection request. When the client needs to establish the connection with the server, it it needs to use a MSocket to set up a MSocket connection with the server. And once the server received a connection request, it needs to accept the connection request. And at this point, the MSocket connection is established from the client end to the server. Then the server can use the MSocket to write a simple message, for example, a hello world message. And uh, here in this case, it's just an example. So the client can use the cellular interface to write the hello message to the server and use the Wi-Fi interface to write the word message to the server. And on the server side, it just simply use a read API to read the message from the MSocket. And it's going to reconstruct the whole message on the server side and get the whole hello world message on the server side. So in the next part, that will show you a demo with an Android application that uses exactly the same abstraction, communication abstraction as shown here. Okay, so before we dive into the progress of like we have made it so far, I'd like to give a brief overview on the mission completion list. So first, as we agreed last year, so we're going to revive the MSocket codebase. For example, adding documents and more package, more applications. So uh, we've done that, and I think we still need to work on it constantly in the future for the other goals, possibly. And the second is to optimize aggregation efficiency uh, through enhanced striping protocol, which is MSocket scheduler. So for that, we found a few related works that have done something very similar to this. And so now it's still in progress, and hopefully we're going to implement a new scheduler for MSocket in the future and show the better performance with the scheduler. And the third one is to advise the fall team to deploy the MSocket on the fall platform. So for that, we decided to use an Android app. Uh, uh, the reason for that is because right now it's more convenient for us to deploy MSocket on a mobile phone. But we are also open to the idea to like shift the code from the current Java implementation to C++ in the future uh, to run the MSocket implementation on the full platform if we can find a reliable Java to C converter. And the last goal is to conduct a measurement-based performance analysis in the wild. Uh, so the lab-controlled experiment have been done by that with the MSocket and MPTCP. In the meanwhile, we also developed an Android app for the future measurement study. Uh, so now I will hand over to Zach to let him introduce the progress we made on the measurement study.
Thank you, Zayu. Hi, my name is Zed, and I will be talking about the following things today. First, I'll show you a demo of the Android application that we built using MSocket API, and this application basically utilizes all the available interfaces on a device to send or receive data. Then I will talk about two different experiments that we did to study MSocket's behavior in the wild. First experiment looks at the overhead of using MSocket in single-phase environments, and then in the second experiment, we look at how well does MSocket do bandwidth aggregation. I have not introduced what bandwidth aggregation means at this point. I will explain it when we get to that part of the experiment. Then finally, Zayu will talk about the experiment in which we use MSocket for vehicle-to-infrastructure communication. Okay, moving on with the Android application. So We developed an Android application that is built on top of MSocket API, and it's capable of utilizing all the available network interfaces on the device. The program flow of the application is quite simple. It sends a request for a certain number of bytes to an MSocket server running in the cloud, and then the server in turn sends that much bytes back to the application. The application then measures the total transfer time and the achieved throughput for the transfer. Server is the server is running in Amazon's EC2 cloud. Now here's the demo. We have a cell phone here that is basically connected to cellular and Wi-Fi both at the same time. And we developed this. So this is an actual phone. The reason you are seeing it on, it's not an emulation. It's just that we have projected the phone's screen onto our laptop screen for the sake of this presentation. But this is not an emulation. It's a real phone. So here's the Android application, and the way it works is that we specify a certain number of bytes. For example, let's say we want to fetch 4 kilobytes from the server, and we want to repeat this experiment for 5 rounds, and then we click on send request. The application is going to fetch the bytes in the background, and then after the transfer is complete, it's going to show us the average results. So what we can see here is that it achieved a throughput of 0.8621 for fetching 4 kilobytes of data, and it took around 41 milliseconds on average for that transfer to happen. What's interesting here is that we can see is that the application used both Wi-Fi and cellular interfaces to fetch this data, and these were the IPs of the interfaces that were used in the transfer. And so if we look closely here, that's done. The application is basically just using 2 interfaces. One thing that I'd like to mention is that the Android by default does not support simultaneous activation of multiple interfaces, so we had to do a few tricks to make this work. One of them was like we had to root the phone and use a third-party application that only works with a specific version of Android to enable both interfaces on this cell phone. This is kind of a hindrance in our deployment process because we cannot just port the MSocket code to any Android phone. It needs to be able to enable simultaneously both of the interfaces. And this is something that we are working on as part of our future plan. How can we make this more easy to enable simultaneous interfaces on an Android phone. All right, moving on. So now let's talk about the different experiments that we did. So first experiment that we did was now, MSocket is good for scenarios where multiple interfaces are available and the application can make use of all of them to achieve a higher throughput than is possible with a single interface, as we will see in the experiments in the next experiment. But we need to ask the question, what happens when there is just one interface available? How does MSocket do in that scenario, and how does it compare to regular TCP? Also interesting would be to see how MPTC perform in a single interface environment. As Zayu explained earlier, MPTCP is an in-kernel implementation, so it's got to have slightly lower overhead compared to MSocket. That's the expectation, so let's see what happens. So here's the experimental setup. So what we did was we developed a client-server Java application, and remember, this is not an Android application; it's just a Java application that runs on any it runs on any JVM, but in this specific case, we are running this application on a laptop. And we made 2 versions of this application. One was built on top of MSocket API, while the other one was built on top of regular BSD socket API. We use a Dell laptop running Ubuntu 16.04 as the host for running the client-side code of these applications, while the server-side code is running in Amazon's cloud. We use 3 different virtual machines, in the Amazon cloud for hosting the servers. One of these machines are running over an MPTCP enabled kernel. Which means that if the client is also MPTCP capable and sends a request to the server, it's going to use MPTCP instead of regular TCP. But if the client is not MPTCP capable, then the server is also going to fall back to using regular TCP. The program flow is quite simple again. The client sends a request for a certain number of bytes, and the server sends back that many bytes. Client notes the transfer time and throughput achieved. Yeah, that's like the program flow. The host laptop runs these three different clients in an interspersed manner so as to minimize the network variation error in the experiment. And then we repeat this experiment for three different flow sizes, and here are the results that we get. So as you can see, this is a CDF of the throughput achieved by each of the three protocols. We see that for 32 megabyte flow size, TCP achieves the highest throughput most of the time, while MPTCP achieves slightly lesser throughput, and MSocket's achieved throughput is comparable to MPTCP in about half of the measurements. We see similar trend for 512 kilobyte flow sizes and for 64 kilobyte flow size as well. And this is sort of what we expected from this experiment. And this is just a more empirical way of quantifying what the overhead was. So here's just a table that summarizes the results from that experiment. We can see that for 32 megabyte, the median throughput achieved by MSocket was 10.54 megabits per second, whereas for TCP it was 10.91, and for MPTCP it was 10.80. And then the trend follows for the rest of the subflows as well, for the rest of the flow size as well. This is a visual representation of the data that I just showed. We can see here that TCP achieves a higher throughput than MPTCP and MSocket and across all flow sizes. Yeah, the average throughput achieved. So yeah, here are just a few observations from the experiment that the median throughput achieved by MSocket is 4.2, 5.7, and 6.7% less than TCP's achieved throughput for the respective flow size of 32 megabytes, 512 kilobyte, and 64 kilobyte. And then similarly, 1.1, 5.06, and 2.67 for MPTCP. It achieves that percent less throughput than regular TCP for flow size 32 megabyte, 512 kilobytes, and 64 kilobytes. In conclusion, what we found from this experiment was that MSocket achieves 5.53% less throughput than TCP, and MPTCP achieves 2.94% less throughput than TCP. Now, these are not very hard and fast numbers. This is just something that we observe in our experiment, and this is reproducible to a large degree, but these can still vary. These numbers can still vary given very slight changes in the experimental setup. Now, having said that, an interesting question to ask at this point would be that whether we can switch from MSocket to TCP. So since MSocket is not doing as good as TCP and it has some overhead, so is it possible to just use TCP in such circumstances where there's just one interface available? So the short answer is that currently it's not possible to do that. The client can, at the start of the application, the client or whoever wants to send or receive the data can decide whether to use TCP or MSocket based on the information that it can get from the OS kernel, whether there are multiple interfaces available or just one interface available. But once the connection is established, when the sockets are open, it's not possible to switch from using regular TCP to using MSocket or vice versa. But this is a very interesting challenge and a question to ask whether we can do this, and not just for MSocket, for any sort of any protocol that utilizes multiple interfaces. So can we switch between that protocol and TCP when TCP is more favorable to use? Okay, moving on to bandwidth aggregation. So now I'll first explain what bandwidth aggregation is, and then I will move forward to explaining what the experiment was. So many modern mobile devices have multiple interfaces, and we can leverage all of the available interfaces to get a better throughput. But it's not a very trivial problem. There are a lot of factors that go into making this happen. For example, what is going to be your striping algorithm? What is the network state at the start of the connection? What is the network state at the mid of the connection? And how fast is it changing? What is the flow size? What kind of traffic patterns are we seeing that the protocol has? So the protocol has to consider all of these factors to achieve the ideal throughput. And since most of these parameters are unknown throughout the connection life, it's not very easy to achieve the ideal throughput, which would just be the sum of all of the individual interfaces throughputs. So the question that we ask at this point is that how well does the current implementation of MSocket achieve this? And to do that, to answer that question, here is our experimental setup. We are again using the same byte stream application that we talked about earlier. The only difference from before here and here is that the client is now connected, the host laptop is now connected to two interfaces, Ethernet and Wi-Fi, and it's going to use both of those interfaces to talk to the servers. And then the host laptop is just going to run these two clients, MSocket and MPTCP client, in an interspersed manner. Like I said, it's almost similar setup to the one described above. The only difference is that the laptop is now connected to interfaces. And secondly, we don't consider regular TCP in this experiment because TCP cannot utilize multiple interfaces, so it's not going to be an apples to apples comparison. And when we talk about bandwidth aggregation, it's really important that we understand that it's we can do bandwidth aggregation for large flow sizes. For a very small flow size, it doesn't make sense to do any kind of bandwidth aggregation. For example, if all of the data can be just sent in one packet, it doesn't make sense to like split that packet across two paths. It only makes sense, for example, let's say when you have 16 megabytes of data to send, then you can send the first 4 megabytes on one path and the next 4 megabytes on another path, and then thus achieve a higher throughput compared to any individual interfaces or individual paths. Having said that, we use these two different flow sizes. One is 512 megabytes, and the other one is 16 megabytes for this experiment. And the results that we get are kind of like this. So here is a CDF of the throughput achieved by MSocket and MPTCP. And for comparison, we also plot the throughput achieved by MSocket and MPTCP when just using Wi-Fi and just using Ethernet, and when MSocket is using both Wi-Fi and Ethernet. So if we just focus on MSocket part, we see that purple, green, and light blue lines are corresponding to MSocket using Wi-Fi only, Ethernet only, and Wi-Fi plus Ethernet. And as we can see here is that the light blue line is actually towards the right of the purple and green line, which basically means that MSocket, when using both Wi-Fi and Ethernet, achieves a higher throughput than when it's using either of the interfaces. And then we see a similar trend for MPTCP as well. The dark blue line is to the right of the brown and the yellow line. And which basically just means that MPTCP is also achieving a higher throughput than either of the two interfaces' individual throughputs. And then we see a similar trend for 16 megabyte flow size. Just some observation from the experiment that both MSocket and MPTCP achieve a greater throughput on the two interfaces than their single interface counterparts. Now, the throughput achieved is not equal to the sum of the individual throughputs, and like I mentioned earlier, it's because of the striping algorithms are not ideal, and we don't have perfect knowledge of the network state. And Yeah, and a few other factors that I mentioned earlier. Now Zayu is going to take over and he's going to explain how did we do the experiment of vehicle to infrastructure communication using MSocket.
Mhm. So thanks that. So another interesting question about MSocket is how it performs in practice. So for that, we did a study on how MSocket in the wild, and it's a similar experiment setup as that shown in the in-lab experiment. So the only difference is that we just actually carry the laptop in a vehicle and drive around with the MSocket client running on the laptop. And we have MSocket client repeatedly fetch 10 KB data from a server running on EC2. The server is in the Virginia region. Uh, and we share a phone's AT&T cellular interface with the laptop, and the laptop itself connects to the EDU room Wi-Fi. Uh, it's a Wi-Fi only available on our campus during the experiment, and we tested three cases. The AMP socket with the Wi-Fi only, AMP socket with cellular only, and AMP socket with both Wi-Fi and cellular. And we repeat the experiment for hundreds rounds and show the CDF as here. So it basically shows that MSocket outperformed at least the worst of the two interfaces in practice, which means MSocket has a smaller response latency than the cellular only, MSocket with a cellular only case. For example, for the 60 percentile, MSocket with both Wi-Fi and cellular has 140 milliseconds latency, and the 60% percentile of MSocket with cellular only shows 180 milliseconds latency. Um, so it does shows like MSocket can improve the performance in practice. Uh, uh, and so next, let's go to the literature survey. So for uh, the for the we have found a few works study the vehicle to infrastructure communication. For example, the relevant paper from last year's Mobicom is also a work from the fall team. And also there's another work from ACMMC last year uh, done by AT&T. And in that work, it shows like the vehicle to infrastructure communication. The size of the data can vary from a few megabytes to a few gigabytes. So for very so as other works has pointed out, multipath communication can really give improve the performance for very large uh, file size. So uh, that's where MSocket can improve the performance for the V2I communication. Uh, and also there's some work have studied the performance, also did a similar uh, MPTCP in practice measurement study. For example, in Mobicom 2016, there's a work shows different applications using MPTCP uh, 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 and shows that some applications can benefit from by using multiple multipath communication, but some application like VoIP and like smaller file size uh, by using multipath, it actually going to degrade the performance. And there's also a bunch of works talk about the MPTCP schedulers. For example, this DMS work scheduler implemented by U Michigan in Mobicom 2017. it actually can achieve a very high performance by sending packets on one pass in the original order and sending the packets in a reverse order on the other pass. And there's also some other works like STMS from ATC 2018 and the RTT scheduler implemented by the MPTCP team in NSDI 2012 study about the cache problem for MPTCP. Like if you have a smaller cache for your application, you're probably going to run into some issue because uh, the networks that cannot deliver the packet to the application, and it's just going to drop the some packet because of smaller cache of the application. And for the R2 plan, in the future, we have a few things in mind right now. So first, we want to do a measurement study with the Android application, and hopefully we can get some workflow from the full team. And if not, we can just use the MSocket Android application to collect uh, the workload in realistic and measure the performance with multipass communication. And second, we can also do a comparison study on the multipass scheduler in different scenarios. For example, like in a lab control environment, what scheduler achieves a better performance, or in a like in a in vehicle environment, like which scheduler actually can show the better performance for MSocket. And the last, we kind of also very interested in the application that can really benefit from using multipass communication. For example, for online video player, if we choose to prefetch the data a lot, then it's probably result into a case that the data prefetched by the video player going to be wasted because the user decide to not watch the video. And if the if the application doesn't prefetch enough chunks, then it's also very risky because it's very possible like the video going to be stalled because you don't fetch enough data from the server. So we also want to use like multipass to communication to optimize the performance or find the trade-off between these two cases. So in summary, we developed an MSocket Android application. And second, we did an overhead analysis for MSocket and the MPTCP in a lab-controlled environment. And we also did a study on the bandwidth aggregation with MSocket and the MPTCP. We also tested MSocket in the wild with a Java application. So any questions?